Hey, welcome back. So far, we've talked in detail about the law of sines and how to use the law of sines to solve oblique triangles. But in this video, we're going to talk about two types of triangles that actually the law of sines out the gates cannot help us with. And here are two examples right here. In this case right here, what we have is an angle, an interior angle between two side lengths. And in the second case here, we only have three side lengths without any angles. Importantly, the question should be, why could we not use law of sines to motivate why we would generate a law of cosines to help us solve these triangles? If we remember the law of sines here, where we're taking the ratios of the sine of an angle divided by the opposite side. Importantly, for any triangle, the ratio is the same throughout the triangle. But the prerequisite when using this to solve a triangle is that we have one angle and the opposite side length. And actually, these are the two cases right here where we can be given three pieces of information about a triangle, but at no point do we have an angle and its opposite side length. For instance, in this case, we have this angle, but we don't have the opposite side length right here. And in this situation right here, obviously we don't have any angles. It will be important for you to recognize when you need the law of cosines, and again, it will come when you don't have an angle and the opposite side, which enables you to use the law of sines. But just to give these labels, we call this a side angle side triangle. And again, we have two sides and the connecting angle in between, or that interior angle between those two side lengths right here. And in this case, we call this a side triangle. And the good news is we actually do have a method for solving these types of triangles. We will use the law of sines, but our first step will be use the law of cosines. So let's take 1 second and derive the law of cosines and then attack solving these two triangles. All right, in order to generate the law of cosines, what I'm going to work with is, again, just a general oblique triangle here. I'm using an acute triangle with no obtuse angles, but the proof is exactly the same either way. It just feels a little bit more pretty when you're working with an acute triangle. And doing this, what we're going to first do is the same step we did when we did the law of sines. We're going to draw a line straight down here from this angle C. This will create two right triangles that we can analyze here. This is important. We're creating a right triangle so that we can invoke our trigonometric functions, our ratios. I'm going to label some information right here. I'm going to say that this length right here is X because it's a horizontal length. This vertical length, I could call it H. We often do that, but I'm going to use a Y right here. Importantly, I want to talk about this because this will be important for the proof. So C is this whole opposite side right here, opposite of angle C. If I label this length right here X, this length right here will be C minus X. So just to give you an overview of how this proof is going to work, it's pretty straightforward. I'm going to find the sine and cosine in terms of these variables that I put here of this angle A. Using that information, what I'm also then going to do is to use the Pythagorean Theorem to relate these three sides. Those two analyses together will give us the law of cosines. So first and foremost, what I'm going to do is define the cosine of A here. The cosine of A is the adjacent side over the hypotenuse of this triangle right here. So I have that the cosine of A equals X divided by B. If I multiply B to both sides, what I get is that X equals B times the cosine of A. I'm now going to do exactly the same thing with the sine of A. So I have the sine of A is the opposite, which is Y over B. Solving that for Y gives me B sine of A. So that's the first part of the proof. Now the second part is pretty straightforward. What I'm going to do is use the Pythagorean theorem on this triangle here. I have my hypotenuse A that's across from my right angle. So what I get in that case is my hypotenuse, or A squared, equals this side length squared, so C minus X squared plus this Y squared. Then what I'm going to do is I'm going to expand this out. Importantly, this is C minus X times C minus X. I'm going to FOIL this out because it's a squared binomial. And what I get is A squared equals C squared minus 2CX plus X squared. I didn't show all that work, but we know of a formula for these perfect square binomials. But also, I get this Y squared on right here. What I'm now going to do is I'm going to replace the x and the y here with these equivalent expressions that I found earlier. So that was the reason for that work over there. And let's see if I can plug these in and not mess this up. I have a squared equals c squared minus 2c times x. X is b cosine of a plus x squared. So if I square this, I got to square this factor and that factor. And so what I get is b squared times the cosine squared of a. And then finally, I have y squared. So that's b times sine of a squared, which gives me b squared sine squared of a. Okay, that looks a little bit messy now, but we're going to apply a really important trick right here. And we're going to do it with these two terms. What I'm going to do, instead of rewriting the whole thing, I'll just factor this b squared out here. But this becomes b squared times cosine squared of a plus sine squared of a. And importantly, this should feel very familiar. Sine squared plus cosine squared of any angle just equals 1. And so in a crazy way, these two terms just add together to be b squared, or b squared times 1, but just b squared for our purposes. Nothing really special can happen here. So I'll rewrite this as a squared equals c squared minus 2. I might as well put the b here first. Minus 2bc cosine of a plus b squared. And that's really it, the magical law of cosines formula. Let me just reorder things real fast. I'm just going to write this as a squared. I'll put this b squared term out front. It feels like it makes it a little bit easier to read. So a squared equals b squared plus c squared minus 2bc cosine of a. Importantly here, and we'll talk a little bit more about this formula and definitely do our two examples with this formula, is that this should feel a lot like the Pythagorean theorem. In fact, in this case, if A is 90 degrees, then we just have the Pythagorean theorem. But again, this is the way you can relate the sides A, B, and C with one of the angles, in this case, the angle associated with this, which is the hypotenuse in our proof over there, and we'll show how to use that. But this relates all of those, and importantly, what this will allow us to do, as you'll see in the next examples, is it will allow us to solve triangles that actually we couldn't solve with the law of sines because we wouldn't have one of those sets of ratios with a side and an angle. And it's important to say that I just proved the law of cosines with a focus on that angle A, but actually you can do the same proof with angle B and angle C. And importantly, we're going to have three different formulas, but I think it's really important just to memorize the structure of this formula. It's a heck of a lot easier than three separate formulas. So if we have a squared here on one side of the equation, that means we're relating with cosine of A, the same angle on its opposite side. So if I do b squared, what I get here are the square of the two other sides of the triangle. So in this case, that would be a squared plus c squared. And then it's going to be minus, and again, these are the same two sides we had here. So in this case, it's minus 2 times a times c, and then times the cosine of the angle opposite of this side length right here, which is b. And then to finish it off, if I had c squared here, this would be a squared plus b squared. And then I have minus 2ab, the cosine of c. All right, let's now use the law of cosines to solve this triangle. Again, when we're trying to solve, we're finding all angles and all lengths of the sides of the triangle. What we have right here, again, just to label this, and again, this is just important to help you with the analysis of when you need the law of cosines. I'm doing a video on the law of cosines, so of course I'm going to use it, but for you, the big question later on in an assessment or something like that, or an application problem is, which do I use, law of sines or law of cosines? This, since it's a side angle side, where I have two side lengths and this interior angle, I need to make sure I use law of cosines because law of sines won't work. There's no combination of a side length and an angle that I know. But after just one step of law of cosines, I then can use law of sines, which is really sweet. So I have this SAS, or side angle side triangle. I need some labels here. I'm going to use this first one. And so I'm just going to label this A, B, and C. And as always, if I label this A, this is length A. B, this is length B, that's angle C, that's length C. All right, so using this formula right here, what I get is that this A, which I'll just put that value right here, what I know is that A squared equals, this is B right here, so B squared, so 10 meters squared, plus C squared, which is 35 meters squared, minus 2 times 10 times 35, so that's all of this jazz right here, times the cosine of that interior angle right here, which is 50 degrees. And then I'm just going to plug all of this into my calculator, making sure that my calculator is in degree mode, because I'm solving these triangles here. And what I got is that A squared equals 875.0487. Then I'm going to apply the square root to get that A equals 29.6 meters. So again, what that gives me right here is this length. So I know this is 29.6 meters. And importantly now, I actually don't need to use the law of cosines anymore to find these angles right here. What I'm going to do is use the law of sines at this point. And importantly, when I do this, and you'll understand this more as you work with these, especially in that case of the ambiguous triangle with the law of sines. What I want to do, just to make sure I find the exact angle for this one, is I'm going to, first of all, use this as my known angle and known side, so sine of A over A. But I'm first going to solve for angle B right here, because I know angle B is acute. I know it's the smallest angle, because it's across from the smallest side. And that's really important if I was looking for this, but if maybe B was an obtuse angle, I'd have to use that 180 degrees minus the sine inverse. I hope this is making sense to you. But just to generalize it, to make your life easier, this is not, you don't have to do this, but to make your life easier, when you use the law of sines right now, what I'm going to do is attack the angle opposite the shortest length, just so I don't have to do any manipulation of 180 minus the sine inverse. So using the law of sines, I get that the sine of 50 degrees divided by 29.6 is equal, I'm going to attack this B right here, so this will be the sine of B over 10. Then multiplying 10 to both sides, and I'll reorder this just so it's easier to look at, I get that the sine of B equals 10 times the sine of 50 degrees over 29.6. And then calculating this in my calculator, again being in degree mode, what I get is the sine of B equals 0.257. Then applying the sine inverse gives me that B equals the sine inverse of 0.257. And when I calculated that, I got 14.9 degrees. So again, that gave me my angle B right here, which is 14.9 degrees. I now have all my sides. I have two of my angles. To find angle C right here, I'm just going to take 180 minus the 50 minus the 14.9. And when I do that, I get 115.1 degrees. And again, this right here is calculating my angle C. I don't need to use law of cosines or sines or anything. I can just use that 180 is the sum of all of those interior angles of a triangle. And just to recap here, importantly, when I went to use the law of sines after this law of cosine step, which is the new part right here, what I went to is attacked angle B. Without getting too into the weeds, it's just always important to remember that the nature of sine inverse and cosine inverse and the restrictions we had to make for sine and cosine to get these one-to-one functions. But the important thing is this, is that I went to find angle B because I know that sine is not going to output an angle more than 90 degrees. The only way to manufacture that an obtuse angle with sine inverse is do the 180 minus. That's actually not the case with cosine, as you'll see in our next example. But I found this angle first, so I can just set that angle, know that angle, knowing that it's across from the smallest side length. It absolutely must be the smallest angle. If I had instead tried to find angle C, it would have taken more work to actually find the angle because the sine inverse wouldn't have outputted the correct angle because this angle C, as you see, weird, was an obtuse angle, and I would have had to do the manipulation that I was talking about. So just my suggestion, when you do this move, when you go to find the use the law of sines to find your first angle, always use this angle across from the smallest side.